All right, example 4 takes a look at a situation where we have radioactive decay. And in radioactive decay, we start out with an initial amount of radioactive material, but through breakdown, decay, it becomes less over time by converting the element into something else. So uranium changes to, I don't know, lead or whatever it is, and we're left with less radioactive uranium after time goes by. So it's decreasing the amount of material through time. Now, when we dealt with population biology, we had our little equation E, K, T, and when K was greater than 0, the population was increasing. When K was less than 0, the population was decreasing. And biologists are used to K being both positive and negative. When the physicists got around to writing equations for radioactive decay, they did it a little bit differently. They decided that they would model it along these lines. dy dt, the change in the radioactive material over time due to decay, is equal to minus kt. Now, in other words, k is going to be a positive number, but there's a minus in front of it, so that the amount of material is decreasing through time. Why didn't they just allow k to be either positive or negative? Well, because radioactive decay always works in one direction, and they wanted to put that minus side out there so that when they solve this differential equation, they get something like y at time t is equal to the amount of material to start with, e to the minus kt. And then by seeing this minus sign out there, it not being hidden within the variable, it's obvious that this is radioactive decay. There's going to be less and less material through time. So they thought that was useful, and okay, yeah, maybe that is useful. So you've heard about the half-life of material. How long does it take for half of the radioactive material to break down and be gone? Well, we can find that out. If we know what k is, we can find that out. We just say y at some time in the future, we'll just make up a number, 1, is equal to, it started out at 2. So if it started out at 2 and now it's 1, it's half gone, is times e to the minus kt. We take the log of both sides. Well, I guess first we should divide through by the 2. So we get 1/2 equals e to the minus kt. We have to take a log on both sides to get rid of this e term. So we get log of 1/2 times log of e to the kt minus kt, but that's of course is just equal to minus kt, like that. And then we divide through by minus k, so we get log of 1/2 divided by minus k is equal to t. That's one way to write it, but it's not the way that it's normally written. You've got to realize that log of 1 over 2 could be rewritten as log of 2 raised to the minus 1 power. And then by rules of logs and exponents, you realize that this minus 1 could be brought to the outside. So this is equal to a minus log of 2. Okay, the minus 1 came out, minus log 2. Therefore, this equation can be rewritten as minus log of 2 divided by minus k is equal to t. But of course, we can rewrite it that way. And in fact, when you find a calculation for the half-life, it's always given in the form where this is a positive number, right? And the negative is supplied in the equation is equal to t. And that's how that's done.